Welcome back to Element 14 Presents. I'm Clem, and this time we're not building one of my project ideas, we're building one of yours. Here on the Element 14 community we have a viewer suggestion, a universal LANC controller for DSLR cameras. That's usually a thing to control the zoom on TV cameras. But I think it's pretty much mechanically and electronically the same as a focus puller, a zoom control. So, okay, he wants this to be smooth and proportional to the amount of input, and also it should be able to actuate big DSLR lenses. So it's usable for indie filmmakers. I think we can build that. Let's try. So why build a focus control system and not just use autofocus? That's exactly the reason why. Focus hunting. Autofocus is not used in filmmaking, it's used in photography. If you're trying to autofocus to a subject, maybe it finds it directly, but sometimes it has to hunt around. Listen to that? It goes back and forth. But in video, you want to have perfect control, so you always go in manual, and then you focus exactly where you want it, and it's a creative decision where to have the focus. And in big movie productions, there's even a job of focus puller. The focus puller only does that. Nothing else. It's only focused on getting focus perfect. And the cameraman is about framing the image. Commercial options that you have are A, mostly really expensive, and B, mostly geared towards real film lenses, which are in general a lot bigger and have a wider throw for focusing than normal photography lenses. So it might be a good option to have an open source variant, and there should be an open source variant of everything, to have for indie filmmakers, hobbyists, enthusiasts, like everybody that doesn't want to spend the big bucks on really expensive, really good film equipment, but still wants to basically film like a pro does. So let's try to build that, make an open source variant of it, put it out there, and hope that this video appears in the credit of some indie movie someday. A while ago, I did make an automatic motion control zoom on this channel. Maybe you've seen the video. It had a few flaws. It was completely wireless, which is pretty useful for focusing these shots when I can't be the cameraman myself. But most problematic with this, you can basically set it, put it to a certain state, and then lock it, because if you would try to make dynamic shots where it zooms in and out or use it for focusing, then you would have the problem of jitter. And we can have that when focusing on a LANC system. We need to have smooth motion and jitter freeness. So we have to make a sturdier construction more akin to what the pros use. You may have seen this contraption in an Element 14 community puzzle post, but this basically is all we need to control the focus. We have a stepper motor this time, not a servo, because this one gives us a reliable exact motion with the same torque in every position. We have a stepper controller, and we have a microcontroller to control the controller. And then we have inputs, so we can control the microcontroller that controls the controller, that controls the motor, and keeps everything in control. So this should be a project that should have the chance to evolve. So what we use as controller is an ESP32C3, because that is basically our microcontroller, and it has Wi-Fi and Bluetooth. So if I want, I can add like phone controls or other wireless controls later. Now I will focus on the corded solution, which is also always very important for people to have. And I want this to be completely enclosed, including the power source, which means it has to run from a single LiPo. Have you ever tried to run a big stepper motor from a single LiPo? Me neither. Let's find out if that's possible. Okay, for this challenge we have to be really selective on the components. So I want to use a standard Nema 17 pattern motor. This one is really heavy. That's like what you use in a 3D printer. And Sanyo Denki makes one that is like a pancake motor, which is same size, pretty much the same torque ratios, but it's a little bit smaller. It's a little bit flatter, like half of this, not even half of that. But it has the same bolt pattern and it has the same electrical characteristics, so it's plenty strong. It's a little bit lighter. We want mass, but we don't want that sort of mass. And then we have a LiPo. A single cell LiPo has 3.7 volts nominal voltage. 4.2 on good days if it's really fully charged. And these are usually run on 12 volts. So you see where the problems come from, right? It's me, your resident dynamic fanboy. So I've used a lot of these driver silent stepstick modules that you can get on Element 14 in a lot of projects. I mostly use the 2130, the 2208, the 2209 ones, and the 5160. That's one good one. And this time I decided to use the 2100 TMC 2100. Why? I've never used that before, but I've studied the data sheet and it tells me that this can run stepper motors with a low voltage of 5.5 volts, which is still a lot higher than 3.7 volts. So there has to be something in between. We have to step up our game and our voltage, mostly the voltage, also the gain. Welcome to KiCad. So I have chosen the ESP32C3 Mini 1 as my microcontroller, just because I know how to use it, used it in previous projects, and it has Wi-Fi and Bluetooth, so in case we want to add to this whole system and make it super fancy, we can. So over here we have an 3.5mm audio jack. That's not for audio, that is where the controller plugs in. The 3.5mm audio jack is basically a standard interface in the video and photo world for external controls for cameras. So a lot of cameras use those jacks, and so why not? People might have the cable already, and you can get the cables cheap. We need to have 2 pull-ups on these lines because they are basically reading the input from the controller, which is an encoder. And that encoder gets fed into 2 GPIOs, so we have to have a known state, and when they're actuated, they get pulled low. This here is ESD protection for this output here. We need a few GPIOs. This is an internal button for controlling if the unit is flashed. Here we have a reset button. I also broke out TX and RX lines just for debugging in case I need those. And then we have here the charger, a step-up converter, and a stepper driver. So our power system works basically like we charge by USB, then that power gets fed into step-up controls, and that power gets fed into the stepper driver. And the logic is all powered by 3.3 volts. So if you look at the charger, you may seen this design a few times before. I've used it in many projects. Not the best in the world, but works reliably. I've used a really tiny 3.3 volt regulator, so to save on space. And this is my USB port, also with input protection here, so we don't have any ESD problems. And here the step-up converter, that's actually the first time I did a step-up converter on this show, and in general I've only done it like once before. Usually step-up converters can have really bad EMI problems. I hope that this one does not, because if it has, then maybe it disturbs the whole operation. So I've basically chosen this part because it's in stock and it allows us to step up a voltage as low as 3 volts to a voltage as high as 5.5 volts. We need 5.5 minimum for the stepper driver, and this chip is available in a lot of versions, and only one of them lets us set that output manually. All the fixed ones are 5 volt max, and the adjustable one is 5.5 max. So we set that to the maximum output with this resistor divider here. That's calculated by a formula in the data sheet. And yeah, that's our motor voltage. And if we go on the next segment, the stepper driver, this is the TMC 2100. The only big difference to the other breakouts that I've used before is that it runs also on 5.5 volts, so it's good for low voltage applications. I've just used the symbol of the 2130, it's the closest by, and the pinout is the same. It's just the inside of those modules is different. So that's the easy way to do it. Yeah, and here we have the controller. The controller is basically just a rotary encoder, and that closes either line A or B, which pulls it down to ground. And the rotary encoder also has a click on it, but the cable that I use only has 3 pins, so basically I can't use the click for anything, but I don't need it anyway. Maybe we make a more sophisticated controller down the line. Okay, here we have the schematic. That gets translated into a PCB, and I've done a little trick. Sorry Isla, who is manufacturing this PCB, but I didn't want to order 2 PCBs. I just order one, and then I'm gonna use my bandsaw and just cut it here. So I have a PCB with the encoder and this 3.5mm jack on it, and that will plug in to this side then in the end. So bandsaw cut instead of ordering 2 PCBs and paying twice for shipping. That's a little hack, sorry. If we look at that in 3D, just need to open it, then it looks like this, and of course I'm missing some models. Yeah, and maybe you recognize this bolt pattern, which is the back side of the Nema 17. So this will be mounted on the back side. Here is all the charging stuff. This is input protection and all the stuff that we need for input output. Here's my USB stuff including protection, and this is where the stepper driver goes, and this whole operation here is the step up converter. Pretty compact. And here we are in the Arduino IDE to look at some code. Ooh, boring, but I promise it's doing the trick. So we have to have a lot of stuff here defined. We don't actually need any libraries this time. Wow. So we basically declare all the pins and some values. We set up serial, which gives us an indication of which position we have reached. So if you want to pull focus to a specific point, you can plug that in, read out serial, and say, okay, that's at position 12. And I want it to go from 15 to 12. Then you just turn until you reach that position and you nail focus every time. A lot of input output stuff, interesting, not really, it's pretty boring. Then we do our multiplier and do our stepping. This delay is basically specified on how fast you want it to move. We can vary that if we want. I haven't implemented any dynamic stuff. That's basically an exercise for the programmers among us. So please help me. Yeah, and this is basically just writing it out to the serial port so we know what's currently happening. This is so handy when I had to debug this thing because the motor would turn only in one direction. but not in the other. And it turns out it was just a matter of current settings. So yeah, let's put that in a case. We have the PCB and the code in place, so it moves, but it doesn't move a lens yet. So we need to button that up, put it in a case that nicely mounts to our camera. And actually, I don't want it to mount directly to the camera, more to the tripod, and then mount the camera and the lens onto that contraption and have it adjustable. So we can, depending on camera and lens that you use, you can basically set the position of our device so that you can either adjust focus or zoom and basically make it fit whatever camera you have, and make lens exchanging and camera exchanging, if needed, really easy. Like the pros do, like professional gear. So what we have here is basically all the case stuff, all this done in FreeCAD. Yeah, free and open source software for the win. So we have a base plate. I will 3D print this in PPG. And then we have this other plate on it that will slide back and forth on this. So the camera gets mounted here. Then these two are connected with thumb screws, so you can adjust them back and forth to align the stepper motor, which will look out of this hole perfectly with the lens that you're using. And then in this cavity over here, this will house the circuit board and the battery. With this hole here, you can basically access all the connections, and the motor goes in here, and through a little plate in between, the cable comes back here and plugs in. And now this thing here is quite interesting. This is my tensioning mechanism. I tried to make a super complicated one with a homemade spring and stuff, and that didn't work like at all. So I made the most simple one that I could think of and take advantage of material properties for that. So as you can see, this is basically just 10 degrees off from a straight line. So two rollers are pinching the belt, and that should hold them in tension. And these parts, like all of these parts, are printed in Meyamakes engineering resin. So all resin prints, but super sturdy, no brittle stuff here. And that material is also a bit bendy. So basically, if I put that under tension, it presses back. So it's like a compliant mechanism, like a inbuilt spring into the case. And that should keep it all aligned and sturdy. Well then, we've got something to do for that colleague over here. Let's print some stuff. That looks like a completed system. I've plugged in my controller with a nice little resin printed case. Also, this is all printed from my own engineering resin, so it's super sturdy. And also these compliant tensioning clamps, they work really good. And if I turn my controller, oh yeah, focus changes. And if I go to the end, it just slips, so I won't break the lens. It just goes right back, and I can focus again. Ah, the sound is great. It's not as silent as the professional ones, but I think that can be solved in software later on. My open source LANC focus control system turned out really good. It's completely enclosed, only powered with a single LiPo cell, which is a pretty big feat to have a single LiPo control such a big motor reliably. The only thing lacking is software. We now have the cable controls, but there should also be an app or something so you can control it wirelessly with your phone. I'm not skilled in programming, but maybe you are. If you would like to help on developing this project further so filmmakers across the world can use it for their indie productions, then go to the Element 14 community, download all the files. You can make this all yourself and build upon it, and maybe we see this used in some cool indie productions. I gotta go. There's another project waiting for me.